Couple quick announcements. So all the quizzes are here. I'm getting, or not all the quizzes here, but all the Unit 1 are in that Unit 1 module, or Unit 2 quizzes kind of pop up within those weeks. I've gotten a couple attempts or questions about attempts, like, oh, I used up all of my attempts and now I'm gonna fail the class. No, tell me, I'll give you more attempts. Okay, not a big deal. I just need to know that that's the case. I did figure out how to get more time and more, well, the time's a bit annoying, but how to get more attempts in. And I did go through and do that this weekend, and then realized kind of after the fact that several people had asked for more attempts, and I didn't actually tell them they had more attempts. I apologize. You all have at least one more attempt if you used up all of your attempts for every quiz, unless you already have a perfect score. So there were a couple cases where I went through and it was like, you've already got a perfect score, I'm not giving you another attempt. If you want one, that's a different matter. You can let me know, because maybe you want it for practice, and I can open that up again. And then time. Time is also an issue. I did try and go through and adjust the time, particularly on ones where people flagged and said I needed more time on this particular one. So I did go through and attempt to do that. Yeah, I think that's it as far as those little quizzes go. Does anybody have any questions about them? On a slightly related note, I want to talk through something about chairs when it looks at cyclohexanes, or when we look at cyclohexanes. That should be good. Hopefully I don't need to be plugged in anymore. If we were to go through and say, actually we'll start with drawing chairs, because lots of people struggle with drawing chairs. Remember, there is a video that talks through how to draw things, or how to draw them. There are a variety of ways to go through and do it. The way that I found was the easiest, whoops, I wanted black, I don't know why it matters. But the easiest for me was to draw two lines roughly parallel to each other, sloped the direction you want your chair to face. So I want the chair facing that way. Cut the net drawing in half, and then look at each half. So if I look at the left half, which line appears shorter, the one on top or the one on bottom? The one on top, which means I'm going to draw my line up. Okay, I'll then connect to the other side. I look to the right half, which line appears shorter, top or bottom? Bottom, which means I'm going to draw down and then connect. I now have a chair. Okay. The next thing I noticed was confusion about how to reference where hydrogens are located. Okay? And that is a very challenging topic. Most students do appear to be able to acknowledge, we'll call that a black bond, and we'll call this a green bond, are axial and equatorial positions. Once they are drawn, spot on, perfect, not an issue. Okay? The issue becomes, number one, how to draw them, right? And then number two, how to interpret it if it isn't actually drawn. Right? And so there's two approaches on that. It isn't actually drawn. You have to be able to visualize it in your head. Okay? And I'm not trying to say this to be mean, but if we look at exam one was all about how we visualize structures and how we represent them. Okay? That was not a great exam average, which means to me that we all need more practice visualizing those things. That means you should be using a model kit, or you should be drawing these things out. You should not be visualizing them in your head. Okay? So if we were to go through and look at this, we'll call this position A. Okay? Position A has two hydrogens located on it. Okay? And if I ask, at position A, is the bond aimed down, equatorial or axial, we've got a bit of a problem. What's that problem? Do you see the bond aimed down? No. Okay. And if you can't see it, therein lies the issue. How do you identify whether it's axial or equatorial? Okay. So step number one, draw it. Okay? And if you're bad at drawing these structures, okay, when it comes to finding questions online, put your paper on the screen and trace the drawing. Okay? That's your number one approach, because now you get an accurate computer-generated drawing as opposed to you trying to draw it by hand. And drawing it by hand, quite frankly, is very, very challenging and takes lots of practice. You probably don't want that lots of practice, so deal with just tracing it on the image. Okay, the next part is we have to draw on the bonds at position A. By definition, there are two bonds, because we have two shown. One must be equatorial and one must be axial. But how we draw them is going to change our ability to interpret at that individual spot. Your axial bonds are perhaps the easiest to identify. Bless you. These are up and down from the point. Okay? And that can be kind of vague, so let's walk through what I mean by the point or our triangle. If we look at this position, see that green triangle? Where's that green triangle aimed? Okay, so this is fun. Okay, I just asked where is it aimed, and I literally got 3 different answers. And that's not counting the silence as an answer also. Okay, I got down, I got axial, okay, and then I got another answer that I already forgot off the top of my head. Okay, so the way that I would think about this triangle is imagine it poking you. Where do you need to be for the triangle to poke you? Do you need to be above the triangle or below the triangle? Above, which means the triangle is pointing up. Okay? This means your axial position needs to be pointed up. Okay? Axial, think axis. This is straight up and down. Okay? Yes, that can be a weird statement, but our up and down is just up and down on our paper. Okay? Why does that become a challenging potential thing to look at? Let's see if I can pull this off. Is that still a chair? Yeah. Where's up and down? Up and down it now isn't straight up and down on our page, the top of the page and the bottom of the page. It's this weird-ass angle on the slope. Okay? So depending on how you draw your structure, oh, come on, let me undo that. There we go. How you draw your structure up and down can be a challenging reference. Okay? This is why it's important to have the chair configuration drawn as appropriately as possible. So our up position is exactly as that black bond is showing. Okay? If I move, let's move here. Where's that triangle? This one here. It's pointing down, which means my axial position needs to be aimed straight down. Usually we break the bond because it's behind. Okay? So we're trying to show that breakage of the bond because this bond is in front of it. We're trying to throw that 3D perspective into it. Does that make sense? If we now go to position A, where's our triangle? Is it aimed up or down? Okay, down. Okay, and this becomes, again, that challenging kind of reference. Okay, you'll note that what changed here is I didn't draw the triangle, was trying to get you to go through and see it. But if we look at our triangle, that's aimed down. Okay, I believe I heard you say at me. Okay, we want to avoid that at all terms. We're only up and down, that's it. Okay, I understand where you're saying the atom of A is. Okay, in our three-dimensional drawing, that black bond from A to, I'll check. I guess I got to put in another later. A to B, that bond is in front of the page. The only atoms that are in the page, try orange. These orange atoms are in the page. Okay? which is another aspect to this. We have to be aware of that three-dimensionality, and ultimately irrelevant to the question we're being asked. We just want axial and equatorial up and down. Okay? So if I looked at A straight down, that would be the axial hydrogen. Okay? I already forgot the initial question. At position A, I said there were two hydrogens. Did I specify up or down? Anybody remember? Well, you two can't remember because I asked before you showed up, so that doesn't work for you two. Anybody else remember what I said? No, that's fair. I don't remember, and I said it. Okay, so let's rephrase and go back to our question. At position A, I want to know the hydrogen that is aimed up. Is it equatorial or axial? So let's look at position A. This bond is aimed down. This bond is also axial. But I asked for the hydrogen that was aimed up. So if you're telling me the up hydrogen is axial, you're wrong. The down hydrogen was axial at position A. Okay? There's two approaches to identify that up hydrogen. One, we drop in the down one and say the down one was axial, which means the other one, by definition, is equatorial. We don't have a choice. It has to be. Okay? Or we go through and we push it all the way. Okay? I want to know the up position. Okay? So the up position, if we push this rest of the way, where's the equatorial? Sorry. Okay? The equatorial definition is a lot more painful than the axial. Okay? Because it's going to start with, it's not axial. That's the definition of our equatorial. Okay? There's a lot of not axial around position A. Okay? So we could potentially argue, depending on how you wanted to go, that this entire space, I could draw a bond and say that was not axial. Okay? But it could get real ugly real fast. Even me drawing that over the top made it pretty nasty, so let's backtrack out of that. Okay? So we'll refine the equatorial a little bit. Okay? It is not axial, but is also parallel to the second bond away. So if this is position A, there's one bond. Everybody see that? Colored that in partially green. Second bond here. Which means if I'm parallel to that, I have to be somewhere on that green line. Where should I be? Should I be on the left side of that A, or should I be on the right side of that A? Why the left side? Absolutely correct. That's where it needs to be.
Because we have one axial down, we need to have one equatorial up.
Okay, so there's an explanation. The axial was down, which means the equatorial must be up. So if we follow from A to the atom, which direction am I moving? Up or down? Moving up. That matches. Okay. The other thing we could look at, number one rule for equatorial was not axial. If I go from A down that dotted line, actually I already said it, which direction am I moving? Down. It can't be axial. And since I've already defined the axial as down at that position, I can't go that way. So if I'm asked the question, is the hydrogen at position A axial or equatorial? That's aimed up. Sorry, we got to add that flavor to it. Okay, we now know it must be aimed. The up one is equatorial, and our answer becomes equatorial. Does that make sense? Does this mean equatorial is always up? No, because it's all based again on where our point is located. And what you'll note is if we look at position A, the point is down. Position B, the point is up, which means your equatorial is going to change its flavor because the directionality of those bonds is also changing. Kind of make sense?
Can you just repeat like your original question?
Unfortunately, I think I keep changing the question, which might be why you need me to repeat it. So I'll try again. Okay. I'll try again, but delete some of this information.
Like, is there already, like, if this was a question, is there already a point drawn on A or no?
The only thing that would be labeled is saying that we're at position A. That is it.
Okay.
Okay. So at position A, I want to know, is the hydrogen that is aimed up equatorial or axial? So if we look at position A, do we see any hydrogens? No, because there's implied hydrogens. You have to be able to know where those implied hydrogens are located.
And the key there is pointing up?
Yes, the key, because I have to know which hydrogen I'm talking about, because there's two. So I have to say, I want the hydrogen that's pointed up, or I want the hydrogen that's pointed down. Because if I don't say that, do you know which hydrogen I'm talking about? No, and you could say either one. Kind of make sense? Okay. To me, the hardest part is, again, those hydrogens are implied, okay? And you have to be able to process where they're located with respect to axial and equatorial. Okay? So there's a spatial awareness, there's probably a drawing awareness, all of those things stack into this. Being able to see and manipulate those is challenging. Make sense? Okay. And for the two of you that came in, I did say that I figured out how to do attempts, increase attempts, and time for individual assignments. You just have to let me know. And of course, I didn't advance this to where we ended. We finished R and S, but that was it, right? Oh, we started right here. I remember that. Okay. Our types of intramolecular bonds. Okay. This, what you'll start to notice, and someone, I already forgot who sent me an email talking, or not an email, posted something about lab starting to appear now in lecture. Yes, now lab is actually going to kick into lecture, and we're going to get some strong kind of overlap between it. Okay, where we started Unit 1 was just how do we see things and how do we draw things. Lab immediately is how do we process it, what do we do with it. Okay, so we're going to start to see that content boil back on us. Okay. The very first thing we now need to be able to do is when we look at those drawings, being able to classify the bond types. Because if we can classify those bond types, we can classify something about their potential reactivity, their interreactivity. Okay. So those definitions are going to become critical. They're going to work the way I want it to. Okay. The next thing that we could kind of think through would be functionality and kind of structure behind these. So if I went through and tried to draw Lewis structures for all of these, okay, which theoretically you'd be able to go through and do, probably not as fast as this, but that's mostly because I've got these structures memorized now. What we might be able to go through and do is draw out these structures and potentially start to think about how they interact with their environment. Okay? You probably don't know much about formaldehyde or acetic acid. You might know something about acetic acid. But you probably know a little bit more about hydrochloric acid or even sodium hydroxide. And I stopped drawing Lewis structure there for the hydroxide. Okay? And the hope would be is that you would be able to draw these structures and then fairly quickly interpret something about their formulas. Okay? And we might be able to use that information to make predictions about their potential chemistry and reactivity. So for instance, the sodium hydroxide comes in with an ionic bond. We might reference that as fairly reactive. Okay? Well, what do you know about sodium hydroxide? There is a metal. Sodium is a metal, yeah. Just in general. You know nothing about sodium hydroxide. What do you know about sodium hydroxide? Has anybody had backed up drains before?
It's a strong base.
Yeah, it's a strong base. We would usually pour it down drains to dissolve all the gunk and trash that's blocking up your vein, or not your veins. Don't do that. Your pipes, your sewer pipes, right? And it would dissolve that, break it down so that you could get free-flowing materials through it again. Okay, so it's exceptionally reactive. Okay, hydrochloric acid. Do you know anything about hydrochloric acid? It's a strong acid. Okay, what about water?
Polar.
Okay, so we might say it's polar. Okay, well, but sodium hydroxide and hydrochloric acid aren't.
Strong base, strong acid.
What does it mean to be a strong acid and a strong base?
High salt in water.
So we could talk about solubility in water. But salt dissolves in water, and if I threw salt water at you, you probably don't care. Why do you care if I throw hydrochloric acid at you? For the record, you should care. It burns. Why? What's going on behind it? Well, there's something about its chemistry. Okay? Its chemistry is so crazy and reactive that we don't just reference it by the name of the compound anymore. We reference it based off of the fact that it burns. And so that if I move to hydrobromic acid, you might also be able to say that it burns. Okay? So we're now categorizing that particular compound effectively based off of whether it burns or not. And we called it acids. Why? Because it's so freaking burny that we want to make sure that people know when we talk about acids, they're dangerous. And we should avoid contact with them. Okay? We can do the same thing with bases. Okay? Well, why are they that scenario? If we look at sodium hydroxide, there's a step out. It's ionic. Hydrochloric acid doesn't have that step out, so that might make it a little bit more challenging. Okay? I heard someone talk about polar. Okay? So the OH bond is polar, right? What was the HCl bond? Polar? Okay? And this becomes a fun term, okay, which doubles back to the lab because people start using polar and nonpolar and just throw them around willy-nilly. What is polar? Define polar for me.
Unequal sharing electron.
Unequal sharing of electrons. Is sodium hydroxide polar? Is formaldehyde? Is acetic acid? Is methane? Okay. Is carbon tetrachloride? Is diethyl ether? And what happens is that in the industry or within the field, we throw around these terms, polar and nonpolar, with some knowledge to support that. And then when someone asks, say, who's learning, and they say, well, why do these things mix? They go, oh, well, they're polar. You don't know that term. And because you don't know that term, you can't explain what that means. So when we talk about polar and nonpolar, you have to understand why and where it's coming from. And if you don't know that, stop using that term. Polar did show up, though, just on the previous slide. But not just polar. What was it in reference to? A polar covalent bond. How do I know I have a polar covalent bond? Right? And if you don't remember, a little bit of shaming here, okay? It is in the slides. You should know that. It is in the lab. You should know that. You're like, but I just started this semester. That was Chem 130, was being able to look and identify those bond types. Okay? And you're like, well, we didn't talk about it that much. You're right. You don't typically talk about it that much, and you focus all on the numbers. Numbers are meaningless without some understanding behind them. Identifying bond classes is massively more important than being able to manipulate the numbers. Okay? So when you look at a structure, you should be able to quickly assess what types of bonds are present, because it will allow you to change your perspective within it. Okay? Carbon to hydrogen. is a non-polar covalent bond. Non-polar covalent. Why? Because there's an equal sharing of electrons. How do I know there's an equal sharing of electrons? None of these molecules except for sodium hydroxide show charge. So unfortunately, that's not going to work out for us.
There's no like, well, there's, I don't know how to explain it, but.
It's electronegativity. It's a difference in electronegativity. That's it. Carbon and hydrogen have almost identical electronegativities. Think back to the very first lecture. There were a couple trends that I told you you needed to know. Guess what one of them was? Electronegativities. Because if you know those trends in electronegativities, you can predict bond types. You can predict, once you know bond types, you can predict force types. Once you know force types, you can predict reaction types. Right? They all stack. Carbon and hydrogen have almost identical electronegativities, which means what happens to the electrons in that bond? They're equally shared. And because they're equally shared, does any charge start to form? Or did you say charge? One of you two said charge. You said charge. No charge forms. And because no charge forms, does it need to interact? No. So when you see nonpolar covalent bonds, what can you do? This is where it can get fun. You can effectively delete it. You don't have to worry about it anymore. Because what are those nonpolar covalent bonds going to do? Perfect answer, nothing. Right? But we have to be able to quickly assess what those bond types are. And if we can't do that, you're relying on memorization. That's where things get dangerous really, 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 really fast. Right? So we want to be able to classify. Once we start to classify, we start to notice reactivity difference. We just deleted it. Okay, that's true, but we want to be able to name it. So we can say, well, they're nonpolar covalent bonds. Well, there's lots of nonpolar covalent bonds. What particular type of nonpolar covalent bonds were they? Right? We could do the same thing with all these other ones. We've got polar covalent bonds between hydrogen and oxygen, hydrogen and chlorine. Okay? But is the reactivity different between those? This is yes, absolutely, Mike, they are, because I don't want hydrochloric acid thrown at me, but I think I'm okay with a little bit of a water. Okay? That chemistry is now so drastically different that we need to further refine those bond types. And what do we further refine them into? Functional groups. Okay? So we take the stuff from Unit 1 and we say, well, if I have a sigma bond between a hydrogen and a carbon, I can know that as an alkyl. I don't say ane because I'm not referencing whether it's ended the structure or not. It's just a piece. Okay? Hydrogen and nitrogen, that's now an amine. Hydrogen and oxygen, hydroxy. Okay? Not to be confused with hydroxide, which you will do, but we'll come back to that periodically. Okay? And this can now start to allow us to classify things and into different pieces. Okay? We can take sigmas between carbons and carbons, pi's between carbons and other things. Could we take pi between oxygen and nitrogen? Yeah, why not? There's a good reason why not. What was this class? Organic chemistry. And organic chemistry is the study of what?
Organic.
What makes it organic?
Carbon. Natural.
Carbon, and not just carbon. Carbon and hydrogen. So could I look at nitrogen double bonding to oxygen? Yeah, I could, absolutely. Okay, and we will see that throughout this semester. Okay, but that becomes less important to us because that bond in and of itself isn't organic, so we don't stress as much about it. Okay? The next part, if we've got these kind of origins for functionality, and I look at this OH, well, I might say that's a hydroxy. But what happens if I put that hydroxy near another functional group, say the carbon-oxygen double bond? Do those functional groups interact with each other? That's more of a rhetorical question. You don't have to know that necessarily yet. Okay? But when we bring functional groups close enough to each other that they can interact, Does that change their individual chemistry? If yes, guess what you just found? It's less a reaction, sort of gets to that point. You found a new functional group. Okay? If I look at just that, I can talk about it as a hydroxy. But if I bond it to a carbonyl, the carbon-oxygen double bond, now what happens? This is now a carboxylic acid. So I'm going from something like alcohol, okay, fun Friday night, okay? Or drowning exam night, okay? To a carboxylic acid, which is now, ouch, that actually hurts my stomach, I should probably stop ingesting this, okay? That's a pretty significant difference in the chemistry. I want to call attention to that difference in chemistry by addressing it as a new functional group. And that's where we end up moving to the functional groups that you should go through and memorize. Okay? At some point or another, we will talk about each and every single one of these functional groups throughout the semester. If you go through and take any future chemistry class, okay, nutrition, biochemistry, all of them have these functional groups present to differing amounts. Okay? And you're responsible for understanding how those structures change the chemistry of the overall molecule. Okay? Depending on those courses, they may just expect you to memorize the outcome. That's it. Okay? That's fine. You can go through and memorize the outcome there. Okay? The point of OChem is to set you up so that you don't have to memorize that information, that you can now start to build and apply that content and focus on why it's relevant, not just memorizing the pieces. Okay? At this stage, you probably just want to go through and memorize. Okay? So that when you see a structure, you can see something about that functionality. And with that functionality, you can start to make predictions about its reactivity. Okay? That's a bit of a stretch at this point. That's our end goal pretty much for the rest of the semester, is we slap up ethers and say, how would we expect ethers to react? Here's how we can make them. Here's how we can destroy them. All of that. Okay? But at this point, if we understand those bond differentials, the bond types that are present, we can now start to make predictions about what we might see within those pieces. Kind of, sort of? Take that as a yes. So at this stage, it's memorize. You need to memorize these functional groups. Once you've got the functional groups memorized, you should then be able to deal with nomenclature a little bit better. Because in nomenclature, you're responsible for looking at a structure and then being able to name it and assemble all those pieces into the proper order. Some of that is, do you know what those names are? Why do you need to know what the names are? If you look at your ingredient list for anything, does it show structures for anything? No. What does it give you? Names. Okay? And the theory is that when we look at these names, we're assigning a name to a structure because it is easier to type and write that on a label and interpret that on a label than it is the structures. Okay? And the hope is that we have one universal name. Just like humans, right? Okay, my name is Michael. Or Mike. Or Professor. Or Dipstick. Or other unmentionables. Okay? There's tons of names associated with an individual person, just like with chemicals, unfortunately. Most of that has to do with historic aspects. These chemicals, or some of them, were around for so long that what happens? Everybody calls it by the common name, whatever was genuinely accepted for that. So if we look at the compound H2O, horrible compound to discuss because it doesn't follow any of these rules, but it follows the rules from Gen Chem. What is the name for the compound H2O? Water? Is that what you were told to call it from your naming rules? No, according to naming rules, it's dihydrogen monoxide. Okay? And if you really want to play around with things, you can look online for things about dihydrogen monoxide, and you will see lots of people trolling out there with all the health hazards associated with dihydrogen monoxide. Right? And they go, oh my God, we got to get rid of, limit people's, it's motherfucking water. Okay? But as soon as you spin a sciencey name onto it, everybody freaks out. Okay? So names carry meaning whether we want them to or not. Okay? And water is one of those typical examples. Okay? And you said it's water or dihydrogen monoxide. It's not agua. Nobody speaks Spanish. Nobody speaks Spanish. Damn. Okay? Agua is water in Spanish. Okay? You ever bought a water bottle and bought the Aquafina? It's not necessarily just their fancy label name. What is aqua? Water. Okay? So everybody speaks a different language. The point of these naming systems is to make sure everybody speaks the same language. Okay? They did a much better job at it than they did for English or Spanish or French, okay, or Italian. But it's still convoluted and it's still a mess and people still don't follow it all. But that's the point of these naming systems. So I want you to be able to look at these and be able to process some of those names. I want you to be able to look at a nutrition label at a random chemical and be like, oh, that means this functional group is present. Drawing connections to whether that's dangerous or not is a whole nother ballgame, and I don't want you to do that. Okay? But I want you to be thinking about, now I can interpret what these things mean. Kind of, sort of? Okay. You're laughing because why are you laughing? No? You won't tell me? Okay, that's fine. Okay. The next part we would push into is our intermolecular forces. Okay? Intermolecular forces are asking us to pull all of this information, how we have atoms, connecting atoms to different relationships in all of those different systems. Okay? Before we can look at atoms, okay, and this isn't addressed within the slides very well, so we'll switch this up. Really what we're talking about for all science is an attraction between any two particles. That's it. I don't care what those particles are connected to yet. I just care that there's an attraction. Okay? And just like humans, we could rank that attraction from being ultimately single to fully partnered up. Right? Okay, so we could get a huge spectrums of singles. We'll just go, does couples work? Partners, let's go with partners. Okay, and even in that word choice, we're now assuming another thing. How are partners different than couples? Well, where are couples in the relationship? Partners sounds a little bit more formal. They're working on things together to the same extent. So maybe couples are a little bit lower than that. Maybe we've got dating. Okay. Singles probably up here. There's probably something. Ooh, there we go. A recluse. Okay. If you haven't heard of a recluse, it's the crazy person that goes out into the wilderness and just ignores the whole rest of society. Okay? I've encountered a couple in my lifetime and heard stories about some. You go out backpacking and you stumble around walking through the wilderness and you see some dude sitting buck naked up on a tree branch covered in flour, and you're like, what the hell is that guy doing? He brought a 5-pound bag of flour into the wilderness and decided to just live on it. Don't know why, but that's what he did. That's recluse. Okay? That's single, but like actively choosing to avoid all encounters. Okay? So we get different attractions within those. Okay? But there's a difference between dating and singles, right? Because dating, you're trying to couple. Where single, maybe you're not trying. So what we might go through and do is divide this. Okay? And say that this is pairs and this is singles, because I don't have anything better to say. Okay? And then within the singles, we could refine those. Within the pairs, we could refine those. Okay? All of those are different differentiations that allow us to interpret something about that human interaction. Chemicals do a very similar thing, except there's less choice behind it. It's now driving to particular chemical systems. Electronegativity, size being two big contributors to those things. All right? And so when we talk about chemicals, what we're talking about is those attractions. Initially, it goes through and we say, well, we have bonds. Those two atoms have coupled. And then we have not bonds. The atoms haven't actually coupled. And we can go through and define those. So our ionic, polar covalent, and covalent are all about what is actually coupled and the things that contribute to that. Well, the things that we contribute to that are ultimately electronegativity, but since nobody's got time to memorize electronegativities, we come up with cheats behind how we would memorize those. Those cheats are, how do you know you have an ionic bond? Metal and a nonmetal. Okay? That works 95% of the time. Should we throw in an exception? Why not? Do we have a metal and a nonmetal?
No.
Is that ionic?
No.
Yes. How do you know what's ionic? This is now going to fall back to your Gen Chem and what you learned in Gen Chem. Guess what NH4 is?
Oh, chlorine is
We don't need to worry about chloride necessarily. The NH4 is going to be the big one. NH4 is what's known as a polyatomic. What was that word?
Ion.
What kind of interaction are you going to expect from an ion? Okay. So the metal and nonmetal works very commonly, but we do have these polyatomic ions that show up. Okay. So if you see an ion, what kind of bond is there? Ionic. That's in the name. Use it. Okay. How do you know you have a covalent bond? Okay. And that one's dangerous. Okay. I'm lazy. The less lazy way to go through and reference this would be to actually call it nonpolar. How do you know you have a nonpolar covalent bond?
electrons are bound to itself.
Bound to itself is good, not anything else. Well, we haven't defined polar covalent yet. So if you want to do that, we can do that. But I would say already you've got a problem because you said same to same and everything else. Well, that could be kind of challenging. There was another bond type that I said,
Is it SCH?
yeah, C to H, which then means what is the polar covalent?
Oh, is that everything else? Yeah,
This is now everything else. Okay? So if I know my ionic and I know my nonpolar covalent, I've got it on lock, and I can figure out what the polar covalent is. It's just whatever didn't fit in those other two categories. Is this perfect? Absolutely not. But does it get us to that 90 to 95% accuracy? Yeah. Okay? For the sake of this class, following these rule sets gets you 100% accuracy. Okay? That's the point behind it, coming up with these simplifications that can allow us to classify. Why do we want these simplifications? Well, what that then moves to is what happens when we now talk about how we scale beyond the interaction within a molecule to now the interaction between molecules. We have a black and red potential interaction. Which interaction do you think is preferenced? Black or red?
Black.
Okay. What charge comes out of the sodium in the chloride?
The chloride is negative.
The chloride is negative and the sodium is positive, and we know that because the bond type between sodium and chlorine is ionic, because sodium is a metal, and because we know electronegativity trends, chlorine is further to the right on the periodic table, which makes it more electronegative, which means it's going to take the electrons. The chloride's negative, which then means I can scale that out to the other ones. Which interaction is more favorable?
The top.
Pairing the negative with
The positive.
the positive, because our opposites attract. That would suggest we can ignore the bottom interaction. We can run this exact same logic system with any other bond type. And we can start to reason through what happens with them. What kind of bond do I have between O and H? Polar covalent. Okay? So that means the electrons in that bond are being pulled one direction versus the other. Which direction are they being pulled? Towards the oxygen or towards the hydrogen?
Towards the oxygen.
Towards the oxygen, because
It's
more electronegative, which means we could say that's negative and that's positive. That should immediately set off problems, though. I'm saying the oxygen is negative and the hydrogen is positive, which means those are
In the wrong order? Oh.
Ionic.
they're ions. They're ionic, but we said it was polar covalent, not ionic. Okay? So the notation that we shift in is we want to make sure that we differentiate it from the ionic bond, because the ionic shows ions. Polar covalent better not show ions. But it's still in the vein of this chemistry. So how do we adjust? We include a delta in front of that symbol. That lowercase delta says a charge is building, but it has not built. Okay? We're in the process of becoming negative. We're in the process of becoming positive.
Is that
Okay?
partial charge?
This would be known as our partial charges. We could then take that same logic and apply that out with our other structures. And where would I expect that stronger attraction, with black or with red?
Black.
With black, again, because positive to negative. So I can now have some predictive power behind this. That's kind of neat. Would I expect both of those black interactions to be the same strength?
No,
Why not?
because you have partial charges on one side and you have full charges on the other side.
Full versus partial, which means we get a difference in strength. Okay? We might anticipate this one being stronger. Okay? And this becomes an interesting statement. We're throwing on ER. Okay? That does not make this bond strong necessarily. Okay? It also does not make it weak. It's stronger. Stronger than what?
Comparatively to.
Compared to the other one. It's always a comparison. Okay? Before we even bring in, well, I already started it. We'll say weaker than the other one. I want to go back to some of the words that I used here. I said that this dotted line was a stronger bond than this one. I screwed up. Is that a bond?
No.
How do we know we have a bond?
You could say a line, but it's not.
Yeah, it seems really silly. Like, oh, you have to have a line between them. You're not showing a line, you're showing a bunch of dashes, so that doesn't mean it's a bond. You're right. It's a very subtle notational change, but that's all it is. The line represents the bond, the dash is representing something that's not a bond. Because this is looking at the attraction now between separate molecules, not within. This is effectively our singles, this is effectively our doubles. Ooh, that's a subtle change, but that subtle change changes our interpretation of the overall system. And so, because of that, we need new words. We don't want to refer to bonds anymore. We want to refer to this new dotted line as a force. Okay? And we have stronger and weaker. And we could just say stronger and weaker for the rest of it, except that we have other bond types that we could bring in, which are going to generate even more stronger and weakers. So we want to come up with names behind them. What do we want to call let's go with the weaker force here. Okay, and if you're struggling to come up with the name, that's okay. You don't have to stress too much about it. Okay, right here we have a negative and a positive. Okay, partial charges, so they're connected to each other. Okay, kind of like the Earth has a negative and a positive pole, right? And they're connected to each other through the Earth. And it has how many poles? Two. And we might call that a dipole. What's happening over here? It is also a dipole. So what do you think the attractive force is going to be called between them? We weren't creative. That force is now called a dipole-dipole, acknowledging the things that created it. What happens in the other one? What things created it? Ions. So we could call it an ion-ion. Okay? Dipole at least has enough syllables that it breaks up. It sounds reasonable, but calling things ion probably sounds a little stupid. So instead we called it ionic. Why is that problematic to call it ionic?
Because you don't know if it's a bond or a force.
We're not referencing whether it's an ionic bond or whether it's the ionic force. Okay? So somebody, likely who was going through and running the teaching process, said that we need to change the name of that force so we can help differentiate the ionic bond from the ionic force. Okay? And so what they went through and did, in reference to the force, they shifted all together to something called electrostatic. Does that mean everybody calls it electrostatic? No, the vast majority of people call it ionic, and you'll still hear me call it ionic. Okay? But what we're trying to do is clarify the language. When we're talking about that force that's coming from ions, we should be referencing it as an electrostatic force. The electrostatic force is a stronger force than our dipole-dipole. Kind of, sort of? Okay. The rest of the lecture went through and looked at several other examples and again tried to build on what these different things are. And so we end up really with 3 categories for our forces. We get ionic, we get dipole-dipole, and we get London dispersion. Okay, or van der Waals. Okay, you may see another name down here called induced dipole. Literally, that's it, induced dipole, following the same pattern as dipole-dipole. Because what happens is you take 2 things that don't want to interact, and as the electrons get near each other, what do the electrons start to do? They repel away. Okay, so it's effectively a game of chicken. You got 2 cars driving at each other. Okay, one of them veers off, the other one gets to keep moving through. So one of them maintains the negative, the other one, the electrons have peeled off, and because the electrons have peeled off, what are they exposing? The nucleus. And the nucleus is what charge? Nucleus. What's in the nucleus?
Neutral.
What's in the nucleus?
Protons.
Protons and neutrons. And what charge are protons?
Positive.
Positive. So as those electron clouds get near each other, as soon as one peels off, you get a positive, a temporary positive. Now you can see those negatives, and they can get a temporary attraction. Okay? Eventually they continue to pass by each other, and the electron cloud shifts back, and we lose that dipole. Okay? That's why it's called induced. It has to be forced to happen through that game of chicken, and it's very, very temporary and fleeting, okay? Which is why it's very weak. Okay? If we push on actually I think the next slide will do that, so we'll look at that in a second. Okay? As you may guess, though, I also have a 4th thing up here, hydrogen bonding. I said there were only 3 forces. Well, there are only 3 forces. And what the hell is hydrogen bonding?
It's another force, but it's under ionic. It's like
Not.
that's
And see,
one
that's where it's
that's
weird.
one A.
It's under ionic. No, it's not under ionic.
But doesn't it have to be an ionic bond?
Nope. Hydrogen bonding is not an ionic force. It's a dipole-dipole force. But if it's under dipole-dipole, why is it above?
Because it's stronger.
There it is. Hydrogen bonding is a special case of dipole-dipole, but it's stronger than. So when we're looking at this ranking here, this ranking isn't supposed to be showing all the different bond types or force types. It's trying to show the relative strength of them. Ionic being the strongest, hydrogen bonding being next, then dipole-dipole, then London dispersion. How do you know you have a hydrogen bonding force? Well, do you have a dipole-dipole? First establish that. If you have a dipole-dipole as your first step, then you can ask, have you had enough of Mike's jokes? enough of Mike's jokes. Do you have a hydrogen bonded to nitrogen, oxygen, or fluorine? Yes. Now you have hydrogen bonding. Okay? Or perhaps you just like having fun in some organic chemistry. Okay? Now you got hydrogen bonding. You're welcome. I'll be here all day. Applause is not necessary. Okay? Those are things we need to be able to recognize, and we need to know their relative strengths because that changes their overall chemistry. Come on. Okay? What this moves to is this diagram, which for the record you will find nowhere else in the world because it comes from me. Okay? And there's some modifications that need to happen to it. For instance, this should be connected all the way through with red. Remember, the ionic bond and the ionic force is very easy to get confused. Why? Because they're effectively the same flippin' thing. Okay? They're just a perspective difference on it. Okay? And really what we're talking about as a last thing that should go on this is that we should have this color-coded out up this direction as well. Okay? Where we go with our black up here and our black up here. And what we're differentiating, right? Does everybody get what I'm trying to do with the coloring? Albeit painfully slowly? Yeah? Okay. What we're trying to show is that that line was our summary of interactions. That was couples versus singles. That was the relationships between things. Okay? But what we can do is once we've acknowledged that line, is that when we look at where the forces come from, a London dispersion force comes from a covalent bond. If you have a nonpolar covalent bond, there's no charges, which means there's no reason for it to interact, which means we're going to have a very weak force. Increasing strength of interaction. So this is a very weak force with a stupidly strong bond. Interesting. A strong bond is going to generate weak forces. And if I have a weak bond, I get strong forces. They're very heavily intertwined and related to each other. But this is also why biologists get this confused. And they'll go through and say, well, ionic bonds are the strongest. No, they are not. Ionic forces are the strongest. Right? That's why when I look at a salt, it has very high melting points. Right? Because it takes a lot of energy to break those forces. But if I look at a covalent compound, like methane, it boils or turns into a gas almost instantly. Why? It has very strong bonds, but stupid weak forces. And so what we're trying to do is separate bonds from forces from each other. When you look at a structure, you see bonds, and what you're being asked to do is extrapolate that to what that means when it interacts with another molecule. What are its forces? That is a challenging thing to nuance. But that's mostly what we go through and do. We talk about all of these kind of principles, phase transitions, melting points, boiling points. All of those are based off of forces. Okay? Salts have strong intermolecular forces. They have high boiling points and melting points, which means their phase transition is very elevated. If I move to something like methane, okay, non-polar covalent bonds, carbons and hydrogens, that generates weak forces. That means those phase transitions drop through the floor. If I want to talk about vapor pressure, which I don't, okay, viscosity, surface tension, okay, all of those are based off of those intermolecular forces. So we need to be able to think through what forces are. If we move to the more important ones, solubility, okay, solubility is how two things mix. Well, for them to mix, what has to happen? They have to share forces. Because if they don't share forces, what happens? They never mix. They prefer to sit with themselves instead of with the other substance, which is where we encounter like dissolves like. We're talking about similar forces. Like forces dissolve like forces. We can push on this even further into reactivity. Because if I push on something like hydrochloric acid, what kind of bond type do I have there? For it to be ionic, what do we need to see? We would need to see a metal and a nonmetal. Is hydrogen a metal? Nope. Is chlorine a metal? Nope. So it's not ionic. What bond type? What did we decide covalent was? Okay. And I'm going to clarify now, because a couple people have now suggested hydrogen bonding and dipole-dipole. I asked for bond type. Hydrogen bonding and dipole-dipole are on what side of my diagram? They're forces. I don't care about those. I care about the bond type.
Polar covalent.
It's polar covalent. Right? They are not ionic and it's not covalent. Which then means if I move into the force type, what happens? I'm now in dipole-dipole or hydrogen bonding, deciding on how I would classify that. How do I know I have hydrogen bonding? You have clearly not had enough of my jokes.
It's not bonded to FON or...
It has to be bonded to fluorine, oxygen, or nitrogen. It is not bonded to fluorine, nitrogen, or oxygen. It is therefore not hydrogen bonding. It's a dipole-dipole force. Okay? That dipole-dipole force is now a strong interaction. This molecule wants to interact with something else. Because it wants to interact with something else, if I put something remotely negative in here, say like a hydroxide, what happens? This chlorine wants to steal the electrons away from the hydrogen. The oxygen wants to pick up that hydrogen. And we're now running a chemical reaction where the electrons have changed places. The oxygen's electrons are now being shared with the hydrogen, and the hydrogen lost its electrons to the chlorine. That's really wicked. You actually just did a chemical reaction. We changed the location of where sigma electrons are located. That's a chemical reaction. That's what we want to actually move into. Okay. Do you all have questions about any of that? The next part, I think I'm going to ask questions of you. It's your opportunity. Too late. Okay. Melting point and boiling point. So now what we want to do is apply. Okay. I don't think I walked through all of these in the play posit, right? No. I left the top two alone. Is that right? I just did. Oh, I just did 4. Well, that's mean. Yeah, it probably was, because it was like, oh, it's way too long. I gotta just stop. I'm just gonna stop. Okay. So let's look at these. This is inverse order. Did I tell you that in the video? Inverse difficulty. The 4 was the easiest. 1 is the absolute hardest. Okay. Totally unintentional. That's the way it went, and it's just stuck since then. Okay. So let's look at 3. Okay. If we're talking about a higher melting point is based off of what? Bonds or forces? Forces. So if I'm going to decide higher melting point, I have to know what the forces are. So how do I figure out forces?
You draw it.
Higher melting point. Elaborate.
You draw the structure, or you don't need to. I don't know.
You can draw the structure. Some of that's going to come to your comfort, again, with Unit 1. Okay? The whole point of Unit 1 was to minimize some of that ability or the necessity to draw out those structures. Okay? If you feel you need to draw absolutely 100%, yes, do so. So we should relatively quickly be able to draw out our structures. So that's a decent first step, I accept. We said it equals stronger forces. Higher melting point means stronger forces. How do I figure out my forces? What was that? What about the molecule are you looking at? I think looking at the atoms is only half of the picture.
Can you do it by determining their bonds first?
Yes. In fact, that's exactly what you should do. Okay. When we're talking about the strength of those forces, it's those charges. Those charges were based off of where the electrons were located. Okay. Well, the electrons moved around depending on the type of bond that was present. So if we're talking about stronger forces, we're really being asked to look at our structures, okay, and evaluate the bonds that we see. So let's take a look at the red structure. What bonds do we see? Do so. Carbon to hydrogen. What other bonds do you see?
Carbon to oxygen.
Cool. Is that it?
Just repeats of that.
And then just repeats of those. Okay? So what kind of bond is there between carbon and hydrogen? That was nonpolar covalent. What kind of bond is carbon to oxygen? Polar covalent. For the record, you need to be a heck of a lot faster nailing down your bond types. Okay? That takes practice, but I'm trying to point out where the weakness appears to be so that we can work on it. Now that we have those bond types, we can now take them to forces. What kind of force do we see for a nonpolar covalent? Nonpolar covalent leads to London dispersion forces. Polar covalent leads to dipole-dipole. Okay? We did a lot of talking, or rather I did a lot of talking. You did do some talking too. Okay? And we think way back earlier, probably about minute 20, 25 within the lecture, and we're now at 67, apologies. Okay? When we looked at those functional groups, or those drawings of structures, I said if we look at this, we could go through and we could just delete this molecule from it. We could delete that molecule from our conversation because it was all what type of bond? Nonpolar covalent. And the nonpolar covalent don't interact. Which means when we go through and do this evaluation, what could we do with that nonpolar covalent bond that we just identified at the bottom? We could ignore it. And so now when we think about the forces exhibited by this molecule, the strongest force coming out of this is dipole-dipole. I could do the same argument for the next structure. We're going to have carbon to hydrogen and carbon to oxygen and oxygen to hydrogen and carbon to carbon. The carbon to carbon and the carbon to hydrogen are both nonpolar covalent bonds, which is going to lead to London dispersion forces, which is all exciting for me to write because what can we do with it now? We could literally delete it. Okay. For the record, it's going to come back and bite us in a second. Okay. We can now look at the carbon to oxygen. What kind of bond is that? Nice. What kind of force? Oxygen to hydrogen. Polar covalent. I didn't ask a question, so I accept the slow. What kind of force? Okay, fair. Okay, and for fair, for the recording's sake, okay, you said hydrogen bonding. I would argue that you should say dipole-dipole. Once you have identified dipole-dipole, you can also acknowledge that you had hydrogen bonding. Okay, what does this mean for us? What is the strongest force in our second molecule? Hydrogen bonding. What is the strongest force in our first molecule? Dipole-dipole. Which one has the highest melting point? The right one. Is that true? Yeah. That's pretty wicked. We can make an interpretation of the actual experimental physical observations just based off of interpreting structures. That's amazing. And that's what we're trying to get to. Okay? For the sake of time, you're going to do 2 on your own, so I'm going to delete it. And instead, we're going to look at 1 together. What kind of bonds do you see in A? C to H? I said bonds. I have C to C. Okay. You said C to C. Everybody else kept their mouth shut. Why do you see C to C?
Just because based off what we did before.
And you're not wrong. That was very accusatory. I'm sort of sorry.
I
Okay.
just kind of like, figured that.
Once you're used to having drawn out structures, hopefully when you see that formula, what you are seeing in your head is this. Is that what you're telling me you saw?
It's based off of my idea.
Okay. Which means there are C to C. Does that make sense?
Yes.
Okay. And that, Kimball, is what we would like to get you to. Okay. It takes way more practice than I will ever admit. Okay. So don't feel bad if you have to draw out the structures. And sometimes your formula is going to be so gross that you wouldn't be able to interpret it from the line formula. Okay. So with both of those, what forces do we get? Or sorry, bond type. Nonpolar covalent, great, which means what bond type? London dispersion forces. And because we said London dispersion forces, what could we do? We could delete it. Oh, I'm so going to regret this. What bond types do you see in the next one? C to H, C to C, both of those are nonpolar covalent, which means London dispersion forces, which means what can we do? Delete it. Which one has the strongest force if we've deleted everything?
Would it be B based just off of surface level?
Okay, so when we're talking about this force, our first approximation is the strength of the force. Okay, did I talk about the fighting little kids in the video? I never know when I talk about that or not. Okay, and I know it sounds a little weird, but we're going to go do it anyway. Okay, if we had, you're now faced off between Dwayne "The Rock" Johnson or a 2-year-old, and you have to choose, you have to fight one of them.
Oh yeah, you talked
said
about
it
this in
lab.
lab.
Yeah, who are you going to fight?
The 5-year-old.
Okay, that one's going to be an easier battle to win. That's the strength. But if you now look at the number behind it, that 5-year-old, now maybe there's 20,000 of them. Are you going to fight The Rock, or are you going to fight 20,000 5-year-olds? Okay. Your argument changes. Okay? And your argument changes not based off of strength or raw strength, because The Rock is still stronger than any individual 5-year-old. But there's a whole hell of a lot more of those 5-year-olds, perhaps with more teeth, to make it all the more painful for that process. So you shift your analysis. So when we're talking about melting point and boiling point, where we start is that very big first surface level. What is the raw strength? That's the type of force. After that, we can move to an amount of force. Okay, is how I would typically reference it. Okay? That amount of force is better referenced as surface area. Okay? So if you go through and read the background information within the textbook for talking about this, they'll make reference to branch chains having, I have to think through it, branch chains having lower melting points and boiling points than straight chains. Okay? You go, oh, I got to memorize straight chains. You don't have to memorize straight versus branched. What changed? If I have a 4-carbon chain versus a 3-carbon chain with one branch off of it, what changes? I have all of these points where I can make contact with another molecule. All of those contact points have to be broken when we talk about melting point. If we move to the other molecule, this carbon is now stuck in the middle. It loses its ability to make a contact point. That lost contact point means less forces. So it's a surface area argument. Okay? With that, I have to be done. Apologies.